Dear students, we'll be discussing on the chapter The Solid State, Part 1. Students, just take some time to look around you. When we look around us, we find a lot of things, and these could be solids, liquids, or gases. However, have you noticed this? That we are mostly surrounded by solids? And we also make use of solids more often than liquids and gases. See, these solids find a wide variety of applications. Each solid is unique in its own way. While a wood is an insulator, metal, which is also a solid, is a conductor. Why do we see a difference in their property? Is primarily because of the nature of the constituent particles and the forces operating between them. They are different from one another mainly because of the structure. This is why the correlation between the structure and properties help us to discover new solid materials with desired properties such as high temperature superconductors, magnetic materials, biodegradable polymers for packaging, and biocompliant solids for surgical implants that will not degrade over time while they are implanted in body. Let us now recall on the three states of matter, that is solid, liquid, and gas. These are different from one another mainly because of the arrangement of constituent particles. In solids, as you know, constituent particles are compact and closely packed. Force of attraction between the particle is maximum because the kinetic energy in case of solid is minimum or the least. As we move from solid towards gas, kinetic energy possessed by the particle is maximum and therefore force of attraction between the particle is the least. With this idea, as you look into each of these states of matter, that is solid, liquid, and gas, stability of these substances depend upon the net effect of two opposing factors like intermolecular force and thermal energy. Intermolecular force always tend to keep the molecules closer. That is why intermolecular force being very strong in case of solids, solids are compact, while thermal energy tend to keep the molecules apart, which is obviously observed in case of gases. Now, with enough of this idea, let's move on to the general characteristics of solid state. Solids have a definite shape, mass, and volume. They are rigid and incompressible. Intermolecular distances are short. Intermolecular forces are strong. Now, in solids, particles have a fixed position. However, they can oscillate about their mean position. Students, this is why solids exhibit a property of rigidity, while liquids and gases are called fluids since they exhibit a property of fluidity. Moving on to the classification of solids. Solids are classified into two types as crystalline solids and amorphous solids, and this classification is done on the basis of nature of order present in the arrangement of constituent particles. So let's take each of these and learn them in detail. The first type is crystalline solids. Crystalline solids consist of a large number of tiny crystals. They have a certain set of properties that we will go through one by one. The first important property is that Crystalline solids have a definite characteristic geometrical shape. They have a definite characteristic geometrical shape. The second property is they have an ordered arrangement. The constituent particles are ordered. They have a certain discipline in their arrangement. And if you can carefully observe the picture, you find that the silicon and the oxygen atoms are arranged in a certain pattern that keeps repeating over the entire crystal periodically. And this is why crystalline solids are said to have a long range order. This is an very important property. This means that having a long range order means that there is a regular pattern of arrangement of the particles which repeats itself periodically over the entire crystal. Moving on to the next important property, that is crystalline solids have a sharp melting point. What do we mean by having a sharp melting point? Or what is meant by a melting point? It is a point at which a solid melts into a liquid. A point at which a solid converts into a liquid. And by saying sharp melting point, we mean to say that when it comes to crystalline solids, this kind of a change happens at a fixed temperature. What you can see here is a graph which represents a cooling curve. And this cooling curve for crystalline solids show two breakpoints at a point A and B. Just to give more clarity on this, you have a line which represents liquid here and this line represents solid. And the line AB, what you can see there is the liquid cooling to form a solid. So at the point A, solidification begins and at the point B, solidification ends. And you can see that that line is parallel to the x-axis, indicating that at a certain time, temperature remains fixed when solidification is happening. It is the same when you take it the other way round. And this is the reason why we call them as true solids. And this is the exact reason why crystalline solids have a definite and characteristic heat of fusion. Now, what do we mean by this heat of fusion? Heat of fusion is nothing but the amount of energy that is required to bring about a change in the unit mass of a solid to a liquid. Let's move on to the next property now. Crystalline solids are anisotropic in nature. What do we mean by this? This is also an important property, students. Crystalline solids are anisotropic in nature. What do we mean by this? It means that some of the physical properties such as thermal conductivity, refractive index, electrical resistance, mechanical strength, such properties, these show different values when measured along different directions in the same crystal. So you take a crystalline solid. This is a small representation of the particle arrangement in a crystalline solid. And you can find there are two lines AB and CD. They simply mean the direction along which the measurement is done of any given physical property. So let us now look at the path AB. Now when you move in the path AB, you find that there are particles that are kind of blue in color, which means they are one kind of a particle and they are all similar. Now let's change the direction and move along the path CD. You find that there are particles in blue color as well as you find particles that are in circles of red color. That means you have two kind of particles along that direction. And this is why when we measure A given physical property along different directions within the same crystal, when it comes to crystalline solid, they differ. And this is a property of anisotropy. So being anisotropy means physical properties when measured along different directions show different values. And this is a clear evidence for the disciplined arrangement of constituent particles in crystalline solids. Let's proceed with the last kind of a property, that is, if you take crystalline solid, say for example diamond, when it is cut into two pieces, you will find that the newly generated surfaces are plain and smooth. This is one of the feature of crystalline solids. Let's now proceed with amorphous solids and moving to the first property now. Unlike crystalline solids which show a definite geometrical shape, these do not have a definite geometrical shape. The second property is that the arrangement of constituent particle, yes, it is ordered, but it is of a short range order. Why do we call it as to be a short range order is because the particles, they are arranged in a regular pattern only over short distances. It is not observed over the entire crystal. So, amorphous solids have a short range order simply means that there is a regular pattern of arrangement of particles which repeats itself periodically over short distances only, not over the entire crystal. The next property is amorphous solids do not have a sharp melting point. Now take a look at this cooling curve. You find that this cooling curve for amorphous solid is smooth. This simply means that when it comes to amorphous solid, there is no such fixed temperature at which it will convert into a liquid. Rather, it would soften over a certain range of temperature. It can be made crystalline by slow cooling of its melt. Also, it can be blown into shapes. So, amorphous solids also are kind of easy to, they can flow. Not as easy as liquids. They move slowly, but they can flow. This is the reason why we call amorphous solids as pseudo-solids or supercooled liquids. So let's take a look at why we call them as pseudo-solids or supercooled liquids. It's because amorphous solids soften over a range of temperature. They can be molded and blown into various shapes. They can be made crystalline by slow cooling their melts. Also, like liquids, they have a tendency to flow. But as I told you, they move slowly. And this is the reason why we call amorphous solids as pseudo-solids or supercooled liquids. If you have observed the glass panes fixed to the windows or doors of old buildings, they are invariably found to be slightly thicker at the bottom than at the top. This is because over the years, glass melt and they slowly move downward, because of which it becomes quite thicker at the bottom than at the top. This is one of the way of looking at amorphous solids, not to have a sharp melting point. Now this is the very reason why amorphous solids do not have a definite heat of fusion. The next property is amorphous solids are isotropic in nature. Take a look at the reason why we call it as isotropic is because physical properties show similar values when measured along different directions in the same crystal. And the physical properties, I mean to say, some of these like refractive index, thermal conductivity, electrical conductivity, mechanical strength. Now, why do we observe similar values when measured along different directions here? is because these solids do not have a disciplined order of arrangement. So you move in any direction, all in all, the particles that it would encounter or the path that you would mark, all in all, it would compensate and finally gives you an end result having a same value no matter you measure in different direction. It's as good as being in a crowd and trying to hunt for different kind of people, maybe a particular kind of group. You will not find when it is in a crowd. No matter in which direction you go, it almost looks the same. So likewise, in case of amorphous solid, this kind of a situation happens, because of which we observe that they show similar values in several directions. Now, the last property is that when amorphous solids are cut into pieces, they come up with the newly generated surfaces that are irregular. Moving on to the applications of solids. Now, let's take a look at this table salt, which is sodium chloride crystal. It's a crystalline solid. And all of us know that it is an ingredient that is used in cooking. It is widely used in food industry as a food preservative, as a flavor enhancer. And sodium in sodium chloride is like an electrolyte that helps to regulate the amount of water in body. So it finds a lot of biological application as well. And industrial manufacturing of chemicals like sodium carbonate, sodium bicarbonate, which you have learned in the last year. Moving on to the next kind of a solid, that is diamond. We know that it's used in jewelry due to their shiny luster and durability. It's hard, and this is why they are used to drill, grind and cut materials. Also, we know that these diamond dust are used in beauty products in case of facial. Moving on to the next kind of a solid, that is quartz. Now quartz is also polishable, it's hard, it's a crystalline solid again. So it's used in jewelry and as a gemstone. Okay, and it is used in glass making, used in clocks and watches. And it has a very high melting point and is chemically inert, because of which it's used in making crucibles that are used in the laboratories for performing chemical reactions and tests. Moving on to the next kind of a solid, that is our quartz glass. These find application in houseware, laboratory ware, construction. These are the inorganic glass that we're talking about. Moving on to another well-known amorphous solid, that is rubber, which is used in making tires, shoe soles, etc. And we also have amorphous silicon, which is one of the best photovoltaic material that is available for the conversion of sunlight into electricity. So these are a few of the applications of different kinds of solids. Let's now once again look into the differences between crystalline and amorphous solids. So moving on to the shape first. Crystalline solids have a definite characteristic shape, while amorphous solids have an irregular shape. When we talk about melting point, crystalline solids have a sharp melting point, while amorphous solids gradually soften over a range of temperature. Simply means they do not have a sharp melting point. Speaking about its nature, crystalline solids are true solids, while amorphous solids are pseudo solids or supercooled liquids. Moving on to the order of arrangement of the constituent particles. Crystalline solids show a long range order, amorphous solids show a short range order. Talking about anisotropy, crystalline solids are anisotropic in nature, while amorphous solids are isotropic in nature. And about the cleavage property, crystalline solids, when cleaved, the newly generated surfaces are plain and smooth, while amorphous solids, when cleaved, the newly generated surfaces are irregular. Now let's move on to the next property, that is heat of fusion. As we mentioned, these crystalline solids have a definite and characteristic heat of fusion, while amorphous solids do not have a definite heat of fusion. And examples, as we discussed, sodium chloride, quartz, that is crystalline quartz, diamond. These are a few examples for crystalline solids. When it comes to amorphous solids, plastic, rubber and quartz glass are the examples. Let's now move into the next concept, that is classification of crystalline solids. These crystalline solid students are broadly classified into 4 types. The first one is molecular solids. Then you have ionic solids, metallic solids and covalent solids. The first type, that is the molecular solid, is further classified as non-polar molecular solids, polar molecular solids and hydrogen bonded molecular solids. Let's look into each of these one by one. The first kind, that is molecular solids, as we mentioned just now, the 3 types are non-polar molecular solids, polar molecular solids and hydrogen bonded molecular solids. As the term indicates, molecules are the constituent particles. Primarily, molecules are the constituent particles in case of molecular solids. Let's move on to the first kind of molecular solid, that is non-polar molecular solids. You can find here the noble gases like helium and argon. Also, we find nitrogen and hydrogen. These are the examples for non-polar molecular solids. Carefully observe, helium and argon are monoatomic in nature, so therefore these are atoms. So the constituent particles in these solids are atoms. Okay. However, they are categorized under molecular solids. And nitrogen, hydrogen are molecules. Let's get into the properties of each of these students. Now, to begin with, constituent particles here. Atoms or non-polar molecules are the constituent particle. Atom, as we looked into these noble gases, and non-polar molecule, what we saw in case of hydrogen and nitrogen. Nature of binding forces. With what kind of force are they held? Dispersion or London forces. Weak forces. Weak van der Waals forces. Physical nature. They are soft solids. Why? Because of the weak force. Melting point is very low. Electrical conductivity. They are insulator because they do not have any free ions. And examples, here we have argon, helium, hydrogen, chlorine, nitrogen. These are a few examples. Now you must know that because they have weak forces acting between them, they usually exist as liquids or gases at room temperature and pressure. Moving on to the next kind, that is polar molecular solids. As you can see, hydrogen chloride, this is one example, and we have SO2, sulfur dioxide, as another example for polar molecular solid. As the term indicates, polar. So you have atoms with the difference in electronegativity creating a polarity there. So let us now look into this in detail. Constituent particles in this case are polar molecules. Nature of binding forces, obvious, it is dipole interactions. Physical nature, it is soft solid. Melting point is low. Electrical conductivity, it's an insulator. Examples, HCl and SO2. Again, even these solids exist as liquids or gases at room temperature and pressure. Moving on to the third kind, that is hydrogen bonded molecular solids. So you see here ammonia is an example, water is an example, and we have learnt about hydrogen bond. What is meant by hydrogen bond? Hydrogen bond is a bond that is always formed between a hydrogen atom and electronegative elements like oxygen, nitrogen and fluorine. So you can see here ammonia and water have these elements. So these are hydrogen bonded molecular solids. Let's get into its detail now. Constituent particles are molecules containing hydrogen linked to electronegative elements like fluorine, oxygen or nitrogen. Binding forces acting is hydrogen bonding. Physical nature, they are soft. Melting point is low. Electrical conductivity, they are again insulators. Examples, as we saw, water and ammonia are the examples. So here we complete polar molecular solids. Now let's get into the next kind, that is ionic solids. So sodium chloride is an example. Magnesium oxide here is another example for ionic solids. What are the constituent particles in case of ionic solids? As the name suggests, ion. So therefore, constituent particles are ions in this case. Nature of binding forces are Coulombic forces of attraction or electrostatic forces of attraction. Physical nature, they are hard and brittle. Melting point is very high. Electrical conductivity, they are insulators in their solid state. Observe, ionic solids are insulators in their solid state. However, they are conductors in their molten state or aqueous solution. Example, sodium chloride, magnesium oxide, zinc sulfide, calcium fluoride. These are the examples for ionic solids. Let's move on to the next kind, that is metallic solids. So you find here iron, copper, magnesium. So now let's get into its detail. Constituent particles, positive ions, metal positive ions in a sea of mobile electrons. These are the constituent particles here. Nature of binding force, it's metallic bonding. Physical nature, these are hard but they are malleable and ductile. They can be drawn into thin sheets and wires. Melting point, it's fairly high. Electrical conductivity, they are conductors in solid as well as molten state. Observe this, ionic solids were insulators in their solid state but conductors in their molten state. However, when it comes to metallic solids, they are conductors in both solid and liquid, the molten state. Yes, that is their liquid form. Examples here, iron, copper, magnesium, silver, these are the examples. So they are conductors for an obvious reason, that in metals we find a sea of mobile electrons, a sea of delocalized electrons that are free to move, and these are the reasons for conduction. Let's move on to the last kind of molecular solids, that is covalent or network solids. You find here examples like diamond, quartz, graphite. These are examples. But here I want you to observe one thing, that diamond and quartz are, strong. Okay, they are hard, but graphite is soft. Let's now look into the structure of diamond. So in this structure, every sphere you see is a carbon, and a carbon tetravalent in nature is bonded to 4 other carbon by means of 4 covalent bonds that are strong and directional in nature. So there are no free electrons here. They are insulators. However, let's take a look at this, that is graphite. When it comes to graphite, we find that the carbon, they form layers, and every layer has a carbon that forms like a hexagonal hexagonal structure that come together and form a single layer. Layer by layer, they are held by weak van der Waals forces. Therefore, they can slip over each other. Okay, and they are soft for this reason. And you can observe here, you have learned this in the last year, that every sphere here is a carbon, by the way. Now, every single carbon is bonded to 3 other carbon students. So, you know that carbon has 4 electrons, right? Valence electron. It can form 4 bonds. But in this case, carbon is forming only 3 bonds. So, there is 1 electron remaining that is free. And therefore, exceptionally, in case of graphite, you find that they are conductors, while diamonds, these are insulators. Now let's get into the details of covalent or network solids, because these are giant molecules and they form network-like structure. They are called so. So now let's look into the first, that is constituent particles. Here are, the non-metal atoms. Moving on to nature of the binding forces, covalent bonding. Physical nature, these are hard, as I told you. Basically, they are hard. Melting point, very high. Electrical conductivity. Now, these are insulators, as I mentioned. Examples are, quartz, silicon carbide, and you have diamond. These are hard and these are insulators. However, observe physical nature. It is soft and they are conductors. This is an exception, as I told you, in case of graphite. Okay, in case of graphite, they are soft because, as I mentioned to you, that the layers that you see in case of graphite are not bonded to each other as such. However, they can easily slip over each other because they are held by weak van der Waals forces. For this reason, graphite is soft and it acts as a good solid lubricant, and they are conductors because they have free electrons in them. Okay, so with this we will come to an end. Thank you, students.